Hello everyone. In this short video we'll discuss about the software, the program that we written in Python in a NDE class to measure the speed of sound in an aluminum block. As we can see here, it was just a plate of 3.22 millimeters, and the measurements was taken in a pulse echo. In this configuration that you see, the one transducer that was transmitting the pulse and receiving it, and we recorded 8 echoes, backhaul echoes. So this was shown on the oscilloscope screen, and we want now to plot and calculate the speed of sound. And this is a first video tutorial that shows how to do that in Python. Of course, here I kind of explain the procedure in a pseudocode code. It's an outline for us to see just how we can write this code. So first of all, again, in Python, we have to import our libraries that I did not include in this procedure. And the libraries are, NumPy, numerical, and matplotlib, because we just want to calculate and plot what we are seeing. And then going through this procedure, we can see that I have to import that data file, and I have to mention that in order for this to happen, because I did not for this file, the way I consider that is that the data file that I'm reading, this that you guys see right there, has to be in the same folder with this Python file. Otherwise, I need to put the path there, tell to Python where to search for the data file. So I didn't do that in this code. This is what we do here. In this first step, we import the data, we allocate the time column as the first. If I go here, and I will show you the data, how it looks in Excel, how it was saved. So we have a time column right now here, and a velocity, which was the amplitude of the second column there. So that was what we have to import. So the time column, as we said in Python, the index starts at 0, so not 1. It is the first column but indexed at 0, and the second column is indexed at 1. So that's the waveform that I put there. And I also need to, well, in this situation, I need the dt to put there, and the thickness of the plate to tell there for the speed of sound. So in this first image I started, after I import it, I want to see what I have there, what did I import in there. So if I run this in the first image, I will I will see the waveform. So this is the waveform as it appeared on the oscilloscope screen, and you can see that I have the pulse that was a negative pulse that we transmitted. This is the front surface echo, and these are the 8 backhaul echoes that are recording on the waveform. So that's what I plot. On the third way is to measure the speed of sound, and the third step. So for that, I am supposed to select 2 backhaul echoes and to measure through the procedure that we said, that cross correlation, so that we can basically calculate the speed of sound, the time of flight, extract the time of flight through the calculation. So that's very accurate procedure, the delay in time between echo 1 and echo 2 and any other echo. But if I go with echo 1 and 3, I have to consider that it does 2 round trips, so I have to change that in my algorithm here. So the way we do it is we are selecting a first echo and the second echo, and we zero everything out, and that's exactly in this piece of code that is done. And you can see that I did observe in the class with the other students that basically the first echo will be a good assumption that it starts, if I zoom it into there, you will see that it starts after 1 second. So I want to capture the first echo and zero everything before and after that. So that will be echo 1. And then echo 2, if I take this and move it, it starts at around 2. So that's, I put a marker there that is a start point. I got the index there of that echo, and I zero everything out. I consider the width of an echo of 500 data points. The data points are in here. If I also zoom in, you will see points in there, so there are multiple points in there, so there are many of them. So through trial and error, we figured it out that 500 is a good option. You can use less or more, you still get good results of the speed of sound measurements. So that's in this number 3. Then we plot those, as you can see, we plot in figure number 2, and that's exactly figure number 2 after we selected those two echoes. Echo 1 is in blue, echo 2 is in green. You can see that I zeroed everything out, and now in this section 4 of our code, we are just applying the cross correlation. In other words, we take echo 2 and we cross correlate it with echo 1, and we do a full correlation in that. And in order to get the time, the cross correlation gives us the lags. That's how it is, and it has a double number of points the original wavelength had. And this is how where I'm using the sampling rate, the sampling interval dt, in order to transform the number of lags, which basically are the number of points there, which we said that is 2 times n plus 1 there. So that's how I'm doing it, and calculated the time, the correlation time. And then I want to calculate the tau, which tau basically is the delay time between pulse 1 and pulse 2, echo 1 and echo 2, pardon me. So, and when we do that, we calculate this and plot it. So, and I plot it as the if we go here, it's that's the cross correlation function. So you see that it has negative values and also positive, and if we look at the number of points, is twice times n, 2n plus 1, where n was the original waveform, number of points of the original waveforms. If I zoom into this one, you can see how the cross correlation function behaves here, and I can, in order to get the maximum, I need the time of the maximum. So the time that the maximum is right there, so it will be selected by the software. So that's what I am here doing it exactly. Let me see, I get this index of the maximum there, and I'm using that index to calculate right here the correlation time, I mean the tau, the lag between the two of them. And then after I have that, that's my time of flight, and I can use it again. Here is twice the thickness, so you know that in order for the sound, it will be from echo 1 here, you will make another round trip until the echo 2 is recorded, and then another round trip until echo 3 is recorded, and so on until the signal dies out. So that's why I have to multiply with 2, because I use 2 consecutive echoes there. If I would use echo 1 and echo 3, then I will have 2 round trips, so I have to multiply with 4. And so on. So that's the way to do it. And then I print it, and we can see the result in the shell, Python shell. So the result is 6.42, and this is millimeters per microsecond, as I put it there. That's how we calculate it. If you want to, of course, have meters per second, as it is in metric system, so then you have 6,420 probably 0.7 meters per second. And I hope this is very clear, not complicated. Once you have it, it's very simple to do for other metals. Once you have a waveform, and you just have to modify the thickness, and also modify the way where you select the first echo, the marker where you want to start the first echo, or when you want to start the second, and so on. Hope this is helpful, and I will see that if you understood it in homework that I assigned. Thank you.